So I just shared with you guys the link to the lab on Colab. Okay. Yep. So the lab is quite simple. It's about interpretable machine learning, right? So we'll start a little bit speaking about what we have covered in the first part, basically speaking about interpretable classification models, such as, linear regression and what are they called? No, logistic regression and decision trees. We will speak about black box classifiers and how can we explain them. And then we will do the same thing for regression models, such as, again, linear regression or decision trees, but for regression. And then we'll speak about black box regression, right? The second part will be how to use LIME for basically text data and for image data, because if you're gonna do it for what are they called? Tabular data, then preferably don't use the LIME library, use the Interpret ML, I think it's called, by Microsoft. It's much faster at least. And then the final part would be to look at the code for GradCam because it's very simple to implement, right? So we will just look at how the code is without actually installing some library or something. So we will be doing it from scratch. Do you guys have, everybody has access to the lab?
Yes.
Perfect. So here we will just take a small data set. I'm not sure if the link actually still works. Does it? Let me try. It's connecting. Let's install it. Nice. So let's just look at the data set. I think now it's installed. No, it's still running. Okay, it's still running. Restart in time. So I think this is the Interpret by Microsoft library. I think it's called Interpret ML. It's pretty easy to use. And this is, I think, the GitHub for them, right? So you will find lots of code here on how to basically do a lot of interpretations and how to build different. So this is, for example, decision trees, and lots of videos and external links and papers that explain basically what's happening in their code, right? So it's quite detailed. If you want to come here to their website and check it out, they have very good documentation. Or if you want to go to their GitHub and just look at it, and it's quite simple to use, right? Some notebooks to get you started. But we could just look at the lab for today and look and try to learn from it, right? So this is the data set. So we have a data set with the following, what are they called? Features: age, work class, I have no idea what this is, education number, marital status, occupation, relationship, race, gender, capital gain, capital loss, house hours per week, and native country. And then finally, the income. Is it smaller than 50K or is it higher than 50K? And now we're going to do some, exploration of basically what's going to happen in our data set. So here, the first part of the interpretability is actually the exploration of the data. We're not going to build a model and interpret it. We're first going to interpret the data itself. We're going to understand what are the distributions in the data. So these are the responses of the model, right? So here, this is the response 0, and this is response 1. Not sure which one is 0 and which one is 1. So here we can see that 0 if smaller than 50K, else it is 1. So 0 is the default. There are a lot of people with 0. And here we have a lot of people, very few amount with 1. We have definitely some class imbalance. Now, if you would like to, for example, go to, I don't know, race, and how does it affect basically the distributions, right? So here we can see that the majority of the data set is clearly white, very much unbalanced when it comes to these different concepts, right? Which is not good. And here we could see, for example, I don't know if the ratios are similar, but definitely something that we could look into, right? How age progresses and income. So here we have just a few who are between 20 till 24 and still making above 50K. And the older they get, the more this ratio gets bigger until basically they die, right? Another thing would be, let's look at something here. So marital status, for example, divorced. This is the distribution. Married civ spouse. I have no idea what that is, but never married. So never married people don't make a lot of money. You should get married, guys. Now let's check education. Yep, some college, they make some good money. High school graduates, they make some good money. Bachelors and masters. Okay, so masters have the highest ratio of 50K over, those who are under 50K. And doctorate also are doing well. And professional school, I don't know what that is, but this also looks good. So this is one part to understand basically how the different features are affecting the outcome, right? Are affecting the predicted value that you want to understand. And this is quite useful in cases where you have like unbalanced data set, when you have just things that you would like to understand in general. So here you can clearly see which features are more interesting. So for example, if he is a doctorate, that's already very big good clue to where they are. So if we go to, let's say, I don't know, work class, what is work class? Private. Okay, not very discriminatory, right? Native country. Wow, so the majority of the data set is from the United States. Okay. Let's go to hours per week. And here we could see that the majority are in this range between 35 and 42. And as we go up, really there is no discriminatory abilities here. So this is not a feature that is going to help us that much. Capital loss, let's see. Yeah, so at least this would tell you what are the different features and how are they affecting basically your data set and your outcome. And here you could just build it very simply by interpret.data and get this class called class histogram and explain data. There are different other techniques in the interpret ML that are built to basically help you interpret the data. So if you want to go, let's just check it out right now, right? Interpret.data. What would that be? Data. You know what? Let's just take this one and search for it. Wow, it's a very good search algorithm. Python. Interpret. Wow. Okay. Well, probably the documentation needs to be improved a little bit, but definitely there are other techniques that you could use to basically help you understand your data a bit better. And already this is a good start to understand that you have major class imbalance, you have lots of discriminative features, or you have a specific target audience. So probably whatever model you're going to build on top of this, you're not going to go to, I don't know, to a country like Japan and deploy this model, right? So this model is clearly built for the United States. So this at least tells you what are the things that you should not deploy your model on, the limitations of your model. Even if you have a very good learner, it's just not gonna learn anything useful for these countries. Now let's go to the simple part, which is explaining these simple models. So this is decision tree classifier, classification tree, linear logistic regression, and this is explainable boosting classifier. So this is basically the glass box. Glass box means it is, let's just go here. Glass box means that it is something that you can interpret by default, right? So you know the model. Glass box models are interpretable due to their structure, for example, including explainable boosting machines, linear models, and decision trees. Glass box models produce lossless explanations and are editable by domain experts. Whereas black box models, for example, these are models that we just don't know what they are at all. So it's not like a neural network or something like that, but it's something that we don't even know what it is, right? So it's just a black box model. They haven't told us if it's a neural network, even if it could be even a linear model. We just don't know what it is, right? It could be SVM for all we know. So it's just a model that we have no idea what it is. It's just basically a function that we can call, or maybe an API that we have access to, like ChatGPT or something like that. But we just don't know what the actual model architecture is. And for the majority of the cases, it's usually just neural networks, because even if you know it's a neural network, it's not going to help you that much. So this is basically EBM, explainable boosting classifier. I'm sure you guys have already done boosting algorithms with Professor Khan, but for the sake of repetition, boosting classifier, let's just say it like this, right? Ensemble learning. So this is just like let me just find a good picture. No good pictures for boosting. This looks good. Yeah. So basically you just train model number one. It will make some error. It's small, it will make some error on some, some specific samples. Those samples will have higher weights, and then we send it to the next model. So the next model is basically being trained on similar data, but it's being asked to focus on the errors of model one. And then model three is being trained on the errors of model two. And then model four, so on and so forth. So this way it gives you like a set of models that are being trained to reduce the error of their predecessor, or like the previous model that was trained. And this usually leads to much better results, right? So this is just in simpler terms what explainable boosting classifiers do. So here we can see it just contains a lot of information about like the hyperparameters of this model. These models are exactly copy pasted from from sklearn, but they are added with an extra layer of explainability. So these are like, you can treat them exactly the way you would treat a sklearn model, right? So you can train them, you can use them to make predictions, you can deploy them, you can save them, you can do anything to them the way you would do to an sklearn model. So if you're going to build a model for a company and you are required to basically do some interpretability, preferably just use the implementation that is provided to us by Microsoft instead of the implementation that is provided by sklearn, because it comes already with the interpretability built into it. Here we're just building a global, basically a global explainer. We'll see what global explainers do. So this tells you the mean absolute score of each feature. Let's go, for example, age, right? So this tells you the error as we go basically through this age, right? So for example, I don't know, for a specific, I think we had better one, which is education, right? Doctorate. I think for doctorate, we had like less error for some reason, I think. Like we had much clearer cuts, so it should be, let me go, education. Yeah, for doctorate, at least like the ratio was much higher, so I'm expecting that the error for doctorate would be like much lower, which is kind of good, right? It's quite separating them very well. That's quite nice. And this basically just gives you a summary of basically your error according to the features, right? So let's go to, let's see, for example, if race is doing well. Where's race? Here's race. Yep. So this is race. We got white doing pretty well. Black is also doing pretty well. Okay, so race did, it's not a racist model, so that's good. And here you could see like the combination of, for example, age and what, I don't know what that is, but FN language. I have no idea what that feature name is, but education.
Finally, and it represents how many instances of this class are really here. Like for our case, it's number of people of that type. Like for example, 70,000
Ah,
of men are never married, IDM clerical, not in family, etc.
okay, that's cool. Okay. Final weight. So it's, that's, yeah, that's a good way to read it. Yeah, that's nice. Thank you. And then we could explain, so this is basically global explainability, just helps you understand how basically the different features interact with the model, right? So this is the scope 3, I think. And then we go to scope 4, which is what we're looking for, which is basically local explainability. And this is the explainability, as we said, that the majority of the people will ask, will require of you, right? This is going to be obligatory of you. And for this one, for example, you just take the five first samples in the test data set, and you're trying to explain the reasoning for them. So here, for example, we see a predicted 0, and the actual is 0, right? So that's nice. Predicted 0, actual 0, predicted 1, actual 1, predicted, oh, it's a good model. Well, but let's basically look into why did that happen. And here you could see that the intercept, it's basically the majority here when we go back. So you see that the intercept is the most important feature, mainly because we have a major class imbalance, right? So by default, if I have a new feature that I just don't even know at all, I'm going to assume that it is class 0 and not class 1, mainly only because class 0 is just more relevant, right? So here we can see intercept is the most important feature. Occupation, so for him is other service. That was kind of a clue why this person is not going to get a higher salary. Education, he has low education. Gender, female, okay, that's sexist. Education number, I don't know what that is. Work class is self-employed, so that's again another reason why the model thought this person does not get above 50K. And then we see that some features were helping her in the positive direction. So for example, age is 62. So for people who are old, the model expects them to make more money than young people. And so on and so forth, right? So you could just go on and understand basically how the model made its prediction. I want to see someone who's positive. Let's see someone who's positive. Okay. So for some reason, this model capital gain was like a direct clue that this person makes a lot of money. And I guess it does make sense because this is just how much money they have, right, in the bank. Now we can explain also the performance per basically, if I'm not mistaken, we should have something here that should explain to us how the performance goes for each individual. Well, basically, this is just your what is it called? Your area under the curve, precision over recall, and you can see it like this. I think there is a better way also to see it by like by specific genders or by specific classes and categories, but for some reason I did not include it here. But definitely, it's easy to get also this kind of information from there. The model does look actually quite nice. I'm not gonna lie, it looks very, very good. 92 area under the curve is quite nice. Now we will go to, I think, yeah, so it's still with a glass box, but for logistic regression and classification tree. So these models are I'm expecting they will be a little bit less performant. So here we see logistic regression with an AUC of 90. This was 92. And classification tree was 85, so even worse. And EBM was the best, clearly. Okay. And you can see here the absolute errors, how they're distributing. And some of them are quite high for these, right? Here you could just do some, again, more explainability as we have seen before, just to understand what the age is doing. So for example, this is, I think, a linear model, I hope, right? The first one is linear regression, yeah. So for linear regression, these are exactly the coefficients. These are not like difficult to interpret or something like that. This is not the feature importance per se, but this is directly the coefficients, right? So this is the feature importance and the coefficients at the same time. So we have things like the intercept. So by default, we are like going down. If the education is preschool, so that's like clear sign that they won't be making a lot of money. Never married, again, also a sign that they don't make a lot of money. There are lots of signs that they don't make a lot of money, right? Okay, so doctorate is a good sign. Professional school is a good sign. How about masters? We don't get it. Let me check masters. Education. Masters. Okay. So masters make less money? How? Education. Masters. No, masters looks more one than a zero. So for some reason the model just didn't catch that, but yeah, that's okay. But basically you could just see and understand what is happening in the model and how the model is working and understanding. So here let's take some random country. Well, the majority of that country are just poor, so it makes sense that too. Here, this is another way to understand. So previously, this was, sorry. So previously, here we have seen basically how to interpret linear regression. Now we could see how to interpret decision trees, and the easiest way to interpret them is to basically visualize them first, right? So this is the visualization of our decision tree. And you can understand how each of these features are influencing basically the model. But I think just by simply looking at the decision tree itself, you have all the interpretability that you need. And here we have the final one. I think this is the boosting classifier, and it's a little bit more complicated to understand because it's a bit of a hassle. So Yep. Let's go for race. Let's see what race does. Okay, so you get some scores for each individual one. And this one is just basically to show everything at the same time. I think I will have to rerun everything from scratch. Yeah, let's not do that. Now I think we're changing the data sets. Oh, this is black box classifiers. Yeah, so black box classifiers basically is just exactly the same thing. But before we do that, we just add a PCA just to make sure that everything is like randomized a little bit and there is no more sense of an actual feature or something that the model is doing, right? So this is just make sure that it's much more difficult to interpret. And to do that, we still have the same abilities as before, so we can understand basically the errors of the model. We can understand how local predictability is doing, but we cannot understand how each individual feature is influencing the results, right? So that's level 3, we cannot have it, but level 4, we can easily have it, right? So this is basically an explanation of why we predicted this sample as a 0, right? And the majority of the explanation is basically because of the intercept. Morris sensitivity is a quite nice one, but this is for regression, I'm supposing. Did we go to regression and I didn't notice? No, okay. So here we will use Morris sensitivity, and it's just a way to basically tell us how this feature is influencing basically the model. So previously, as we said, the level 3 is very difficult to actually interpret, but Morris sensitivity is an algorithm that gives us that level 3, even in the case of a black box model. But it's not something that you should just fully 100% trust. It's basically just an estimation, as for example, is here, for example, with Lime. This is just another algorithm that just tells us the sensitivity of the model for a specific feature, right? So that could give us some, let me just pull up the ML interpret book so that we have also the scopes ahead of us. So here is the algorithm transparency. As we know, it's black box, so we don't know it. The global holistic model, how does the trained model make its predictions? Again, we still don't know that because it's a black box model. But the third level, which is global model interpretability on a modular level, how do parts of the model affect the predictions? We could at least get how does the input affect the model, or basically how do the features affect the model using the Morris sensitivity. It's quite a useful technique, but it's not extremely accurate. It's just, again, similar to Lime. It's just an algorithm or a proxy to get what we actually are looking for. There is also partial dependence, which gives you something extremely similar. Just tells you basically how your response is changing according to your age or stuff like that. And that might be able to give you an explanation of how does the, what is it called? How does the age, for example, affect the predictions? Or how does different values of the age affect the actual predictions of the model? And here you could just see all of them together. Here it doesn't work because we're trying to show like a big dashboard. So for example, if you are not on Google Colab and you're using it on for example, your own website, or sorry, on your own laptop, it should give you like a big website where you have all of these, you know, charts and all of these visualizations in the same website, and you can just jump from each to anything that you want to see, right? So it's quite flexible, but since we're not using it on an actual server and we're using it on what is it called, in Colab, it's just not going to show us that yet. Now we go to regression methods, and we're not going to spend a lot of time here because it's going to be exactly the same thing. So here it just tells you how your response variable is. So this is for regression. So in order to do that, we just do some binning. and do a histogram. And for example, for age, it just gives you how everything is like dense, well, the Pearson correlation between them, right? I don't know, something else. What is this? So I only understand age in here. This looks like a complicated data set. So it's the Boston data set. What is load Boston? Let's check it. Load Boston sklearn. So returns Boston house prices. Okay, so let's go back. Yeah, it would make sense that the age is like negatively correlated with the size or with the price. So the older the house is, probably the less expensive it gets, or something like that. Yep. So this is again explainable boosting regressor, which is the same thing, linear regression and regression tree. Everything's gonna be exactly the same as we have seen in basically, what is it called, in the classification part, but instead of area under the curve, now we're showing the MSE and the R squared, which are quite nice. Yeah, they're definitely quite nice. Yep. And clearly, yeah, clearly the boosting regressor is 100 times better than a logistic regression, linear regression. Again, the same thing for the explainability. Both the third level and the fourth level are easily explainable. Explaining black box models, again, we just add PCA and we do the same exact explanations, basically the results explanations, which is the default thing. And then we get, using Lime, we just basically do the interpretation for a singular. So this was very close. This was very far, right? So this was a big error for us, right? The predicted is 21 and the actual is 16. And for some reason, this is the decomposition of how we made that prediction, right? So the intercept is by default at 25 almost. So that's like the mean, I guess, of the distribution of that variable. Let me check. Regression. Yep, here's the data set. Let's look at the summary. 20, yeah, somewhere around here. Yeah, it would make sense that the intercept is that high. So we're not going to be like judging the model for using the intercept as like a reason for why it predicted that feature, specific feature like that. Let me just, I'm getting lost here. Interpretable regression models, and we were speaking about, yes, about this one. Yeah. So here, for example, the predicted is 19 and the actual is 16. And this is, the majority of it is because the intercept was too high, but maybe we're not lowering these negative contributors are not negatively like contributing enough. So maybe we could try to improve a little bit on these different features, right? But as I said, so everything that we have seen before, we can do for everything that we did for classification, we can do for regression. And same thing here, same thing here. Yep. So again, also for regression, we have the partial dependence and the Morris sensitivity. I think Morris sensitivity, at least the way I studied it, is like built for regression. I think it was just adopted for classification in some way, but it works very, very well for a regression. That's a good thing, right? So that was Interpret by Microsoft. It's quite a simple library to use. You could just assume that it is the new sklearn for you if you want to build a model that is interpretable, and just use whatever model that comes with it, and they are all easily interpretable. They have lots of like data exploration techniques and lots of data exploration and lots of like model interpretability techniques, whether it's a black box model or a simpler model that is like open and a glass box model, right? So now let's go to Lime. I'm not going to explain Lime again, right? We already know what Lime does, but I will try to put the slides on, or not the slides. Let's just go to this one and go to Lime. Here's Lime. So just for like a recap, what we will be doing with Lime is very simple. We will generate random samples. We will make the predictions for those random samples. We will get the weights for the random samples and then build a classifier. So let's go to this one. We will install basically Lime, right? It's a simple, very simple one. And here's the data set. It's just a text data set, right? For just like a couple of news articles. The classifier is going to be, I'm not sure if you guys have done natural language processing already, but I think we could do it like next week, I think, right? But basically, this is a TF-IDF vectorizer. It just kind of tells you how many, it's like a counter. Just think of it as a counter of words, a word count. And that tells you basically, so for example, if an article again mentions a lot Jesus or Christmas or something like that, then it's probably a Christian article. And if it mentions a lot of things, I don't know, like what's that guy called? The guy who invented or discovered evolution. What's his name?
Darwin.
Yeah, Darwin. Yeah, exactly. So if it mentions a lot of Darwin, it mentions things like, I don't know, like, yeah, evolution and stuff like that. It probably is speaking about atheism, right? So think about this as just a word count, and it tells you how basically how much frequency, what is the frequency of that word in the document. Just for now, that's what we should think about it. If you guys did some more natural language processing courses, then you probably understand TF-IDF vectorizer much in depth. So on top of that, as I said, the word counter, we will build a simple random forest classifier, right? And it will train on the data set. So here is the accuracy of the model. So this is the F1 score, and the F1 score is 92%, and it's quite nice, right? So the F1 score is quite nice. The model is quite accurate, but this model, we just cannot really understand it that easily. So we're trying to build, what is it called? Trying to build a Lime interpreter or Lime explainer on top of it, right? Because we're trying to interpret the text, whereas this model's input is basically a counter, right? So it's not really something that is easy to interpret when it comes to counting words, right? So what's going to happen now is we will build a model that is like a combination of the TF-IDF vectorizer, and then we will send it to the Lime explainer, and basically the Lime explainer will try to explain to us why did we make such a prediction. So predict probability. Yep, and this is the test data set. All good. Now what we're going to do is we will basically build a pipeline. This is our model, which is basically the vectorizer and the random forest. This is the new model. It's a combination of two different techniques. And then we get basically, we get to interpret this model. So this is the, what is it called? The prediction probability of any data set or any sample. Here we can see that it's most likely to be a class 1. I think class 1 means, Christianity, right? Christian text. And what we just do is we get the Lime text explainer. We give it the class names, which are Christianity and atheism. And we start asking it, explainer.explain instance. We give it the instance, right? We give it the function to make a prediction, and how many features do we want to explain. We'll see later on what this does, but for now, document ID is this one. Here's the probability for being a Christian, 45%. So probably the true class is atheism, and the predicted class was also atheism, so that's nice. And now when we go to the predictability, or why did the model make this reasoning, we can see that it's because of the following words. So a word like edu, probably education related to atheism, university, could be something that is related to atheism. Posting, for some reason, posting was a reason the model thinks it's atheism. And NNTP, what is NNTP? Does anybody know what is NNTP? Network news transfer protocol. So yeah, it thinks that, for example, NNTP is a atheist word. Host, so probably something like, probably like computer science stuff. Now, this might be cool to see it, but it's even cooler to plot it. So this is the explanation as a plot, and this tells you basically what's happening. In here, for example, we can see that university is a word that is a clue for Christianity and not a clue for atheism, right? So here, for example, university is associated by the model with Christianity, whereas things like NNTP, host, edu, and posting, so probably .edu means like it's a website. Yeah, it's like here, you know, the end of the .edu thing, which is like website or something like that, or like an email. Wow, so it ignored the word Darwin. So the word Darwin was not used as a clue that this is an atheist text. Okay. So yeah, okay, why not? So yeah, this tells you that basically either your model is not perfect and really your model does not understand what is an atheist text, or Lime is just not good enough and we should improve a little bit on Lime. And how do we improve on Lime? Very simply, let me just go to the documentation because I don't want to rerun everything again because it's a very slow one. Lime package, right? Here it is. Lime explain instance. And we should be able to find like something that is called, no, not explain instance with data. Explain instance. Yeah, here's, yeah. So number of features and number of samples. So here we see that we are generating by default 1,000 random examples, which for a text data set might not be enough, right? So if you see this text, it's quite a large text, right? Let's go back. So it's quite a large text. And just 1,000 variation is not going to be enough to actually build a good Lime model or a good Lime interpretability on top of this. So we could try, for example, to just come here, explain instance, and say number of samples. Sorry, I should not have done that. Number of samples equal to 10,000 or more. The more, the better. So the more number of samples you add, the more your model will probably pick up on some good indices on why the more Lime will pick up on why the model actually made that prediction. So this is it for text. You can just play around with it as you have seen here. It can tell you, like, put the text here with some highlights on what are the concepts that are, you know, associated with this class, what are the concepts that are associated with this class. And for example, I'm guessing the concept of university, for example, is because we have a lot of like Christian universities, right? So we have University of Notre Dame. Lots of like universities have like very Christian roots. So probably that's like the reason why the model has picked up on the word university with Christian, right? I have no idea why did it not pick up on Darwin as a clue for atheism, but either we will fix it by improving the performances of Lime Explainer, or we should basically work our model a bit better, right? Improve the results of our model. And now we go from Lime for text to Lime for images. It's quite similar. Basically, you take an image. You're going to see a lot of code here, mainly because it's going to be using a, what is it called? Let me check. PyTorch, right? Yeah, it's going to be using like PyTorch to convert the images into, what is it called? So convert the images into tensors and stuff like that. So a lot of this code that you're seeing here, the normalization, I think we have already covered this code in like the first lab, right? So you're already familiar with all of this. But for the sake of the interpretability part, we're not going to explain any of this code, right? So this is just basic processing of the image to convert it from an image to to an actual tensor that goes into the model. So this is a ResNet 18, which is a CNN, definitely something that you cannot easily interpret why it made its decisions. Here, please don't ask me what this code does. It just basically goes here, right, to this JSON, and it tries to build on top of this JSON a list of like understanding what is class 0, name of that class. So here, for example, is class 0 is tench, class 1 is goldfish, class 2 is great white shark. Let's see where person is, right? Person, human, dog. Okay, at least dog, we have it, right? So here we see that, for example, a Maltese dog is class number 153. Shetland sheepdog is 230. So this is just basically a map that gives you class ID to the, what is it called? To the name of that class. So it's just a way to do the mapping from basically the, what is it called? The class index to the class name. That's it. And here it's just going to do, again, some processing for the image. This is batch predict. So this is just a function that we will be using. You take a couple of images, set the model to evaluation, set them into basically a stack of actual, what are they called? Tensors, right? So actual tensors going from images to an actual tensor. So pre-processing them and transforming them into an actual tensor, sending the model to, or sending the data to CUDA, sending the model to CUDA, and then basically running the model, getting the probability of the model, detaching it from, basically detach allows you to detach basically the value from its, what is it called? The calculation of its gradients. So there's no risk of having any gradients being attached in here. So we're just detaching it from all the training or something that you were previously doing with loss functions and stuff like that. So we're just detaching it. We're bringing it back into the CPU because previously we were doing our calculations in the GPU. So we're bringing it back into the CPU. And since we're assuming this is a black box model, we're going to pretend that this black box model does not work with, what is it called? It's not PyTorch. We don't care if it's PyTorch or not. So we're just going to return a NumPy array. So this is just what this does, right? So you take the probabilities and you convert them into a NumPy array in the following order. If you inverse any of these orders, you're going to get a lot of errors. So always detach it, send it out of the GPU, and then convert it into NumPy. And here we will see exactly what happens. So Lime explainer explain an instance. You give it the image. This is the image. This is the test instance. You give it the batch predict function. So this is the batch predict function, the function that the model will use to actually make his predictions. This is the amount of labels that he wants to create, or he wants to interpret, sorry, the top 5 labels that he wants to interpret, hide color, and then this is the number of samples, number of images that will be sent for the classification function. If you want a better model, definitely the number of samples must be higher, but as you can understand, 1,000 passes through a convolutional neural network is going to take a lot of time to calculate. So if you want even better, which means like 10,000 or 20,000, that's going to take you like an hour to get that explainability, right? To get that explainable result. So this is why definitely Lime for image data is, it's just a theoretical concept. It's not something that you will actually be doing in real life, right? And if you are, it's not going to be for like a product, mainly more for research purposes. And here we'll just basically build this beautiful image. You just get the image and its mask. And basically this is just a couple of, to add this segmentation on top of the image. And this kind of tells you what is the interpretability of your model. So here, this is the code that I used to generate that first image in what is it called? In the lecture slides. And here we can see that, for example, it's a Pomeranian. Probably it's a correct class, and it focused on the mouth here and a little bit of the nose and the head a little bit and stuff like that. And the second top class was Persian cat for some reason. I don't know why, but probably they look. But yeah, so it's very, very sure that it is a Pomeranian. Yeah, Pomeranian. Now from line to text dataset and line on images, we will go to GradCam. So remember, GradCam, as we said, is like a very simple concept, and it's something that we could actually implement. I'm not sure if that dude is here. No, he's not here. For some reason, many of you are not here today. Was there like some event in the university or something?
No.
No, so they just didn't show up. Okay. It's such a shame because one of the students last time was like proposing some like changes on GradCam. And if you wanted, then we could just do those changes here, right? Because you have the code for GradCam and it's actually very readable code, like easy to understand if you know the steps for GradCam. So not really sure why. Yeah, but anyway, if you guys want, you can easily just look at this code, understand a little bit more on what GradCam does. So this is like pre-processed image, definitely not something that you should even spend some time on. Show cam on image, also this is basic Python stuff we don't care about. Guided backpropagation value, I don't think this is something that is, yeah, this is not for us, mainly for, it's not for, what is it called? It's not for the default version of GradCam. This is for an extra bonus version of GradCam. And this is just for you guys, right? This is guided. It's like a similar version to GradCam, but it's also guided using, what is it called? Backpropagation. The process image, again, not something that you should even spend some time on. But what I want you guys to see is the speed of GradCam compared to something like Lime, right? So for GradCam, we're not doing any passes through the CNN 1,000 or 10,000 times, right? We just pass through the CNN once, and everything else is just a couple of matrix multiplications and additions, not even multiplications, just additions, right? Just basic additions or summation of a couple of matrices, and that's it. That's all you will be doing in GradCam. So let's look at its code like by default. So here you see use CUDA, it sends the model to CUDA, it just activates the model's evaluation mode by default, meaning if there is things like, what is it called? I forgot the name. Setting like some neurons to zero. What is that called? Neurons to zero. Drop. What is that called? Forgot it. Dropout. Yeah, sorry. So if there is like things like dropout or something, then yeah, so we're gonna deactivate it by activating this evaluation mode. So by default, it just goes to the evaluation mode. This extractor or model outputs. So what it does, if we come to it, is it's a class for making a forward pass and getting the one network output, activations from intermediate targeted layer, and gradients from intermediate targeted layer. So this is a really cool function, right? So feature extractor dot gradients and then feature extractor X. This is the output, right? Well, this is really direct, right? So for the get gradients, you just call that layer dot gradients here. Let me say the gradients, how do they call it? The gradients, register hook, save gradients. But it's a quite direct access to the gradients, I guess, right? Feature extractor, extracting activations, and registering gradients and from targeted intermediate layers. self gradients, here they are. And it just goes through all the model layers one by one and passes through them. If it is the target layer, then it registers it here and saves its gradients. Oh, that's cool. So it's a very simple way to access basically the gradients. We go back to breadcam. No, we go back to model outputs here. So this is how we access the gradients, just by simply accessing the gradients. We go up a little bit, sorry. Yeah. And here we just get basically access to the output of that specific layer, right? This is the target layer that we want. Simply, we just get its output from this call, right? Outputs and X. So X is the final, basically, X is the final version of X, remember? So we take the input, and at each layer of the neural network, we replace that output by X. So basically, the final X at this step is the final output of the CNN. And this is why here it's called output. And here it's called the target activations, because we return basically these, right? So we return the target layers activations. So this gives us the target activations, the output. This gives us the output of the model, just simply by converting it a little bit and just reshaping it. And here is the class model outputs. This gives us both the gradients and the activation function, or the feature map. No, the convolutional feature map at a certain target layer. So this is done. This is the init. This is the forward. It's quite a simple call. And this is the default call for GradCam. If use CUDA, then we just go to CUDA. If not, we don't go to CUDA. This probably just extracts the features and the output, right? So this is the features at a specific target layer and the output of the model. If index equals none, then index equals this. So this means if we don't send what is the, remember, GradCam is class dependent explainer. So if we don't tell it which class it should explain, by default, it will try to explain the class with the highest probability. So it explains why the model made its prediction for the highest probability class. But this is something that we could easily, as we said, change. If you want to understand why the model thinks this picture of a dog is similar to a cat, just send the index of a cat. And how do you get the index of a cat? From this place, just come here, say cat, I don't know, Persian cat, tiger cat, Egyptian cat. Choose any one of these cats and send their index to this function, and it will give you the explanation for that specific class. One hot, this looks cool. Features does Eurograd, classifier does Eurograd. It just makes sure that there is no, what is it called? No back propagation of any error happening at any time, but this probably is not gonna affect it that much, because if you're gonna call it once and if you're gonna like destroy it again, then it's not gonna happen multiple times. But just to make sure that this backward, if you call the same GradCam on multiple images, then you're going to be doing this one hot dot backwards multiple times, and that might give you lots of gradients that you did not want to calculate. Grads value, extractor don't get gradients. Take the mean over the grad values, and then cam is basically the weights times the target at I. So it's the weight, so it's the average, right? So it's the average of the gradient map at that specific layer multiplied by the actual value of that, multiplied by the actual feature map of that target here. So we have, let's just go back to GradCam. I think it's mentioned here somewhere, GradCam. Let me check. Okay, so he does not mention it. Then let's just go to the lecture, or just go here, GradCam. Okay, so this is the image that I want. Let me zoom in. Yeah, so basically it does this. First, it calculates the gradients of this specific class with regards to a certain feature map. And then it takes the mean of those and it multiplies the mean with each one of these convolutional feature maps. And then it takes the sum. Yeah, so it just keeps on taking the sum inside this cam variable of the weights, which are just the mean of the gradients, times the actual what is it called? Convolutional feature map, the value of the convolutional feature map. I think the guy last time was proposing, instead of taking the mean, we take the maximum or something like that. But since he's not here, then I don't think we can experiment with what he wanted to see. Basically, this is just making sure that the numbers are just in a correct scale that we could use, right? So this is useless for us, right? So this is basically, what is it called? The final step, yeah, ReLU. This is ReLU. It's just the maximum between the actual value and 0, which is the definition of ReLU. Instead of just calling it ReLU, we're just defining it a bit simpler. And this is just to make sure that we can actually see see it in an actual image, right? So it's not something that has some weird values in it. And yeah, that's it. You just take an image, pre-process it, call GradCam on it. For us right now, the target index is none, but we can easily change that and basically see what the model does. So here is the reason why the model thinks that this is a dog. And for some reason, it focused a lot on the eyes, right? So for it, the eyes are the clue that this is this exact specific breed of dogs. I'm not a dog expert, but this just seems reasonable enough to me, right? These two are what we call, it says this is the gradient backpropagated, or forgot the name. Guided backprop. Yeah, this is the guided backprop, and this is the cam / guided backprop. So it just tells you what the model is looking at. And here we can clearly see that the model does not focus on the background. So if you look at the image here, we can see a lot of background here. And using this, we can clearly see that the model does not focus on it. It only focuses on the face of the dog. And this is a good index, or a clear index, that your model is actually doing something useful, that the model has actually learned something good. So GradCam is something that would allow us to get the third level of interpretability, the fourth level of interpretability, or the fourth scope of interpretability, but it is something that you should like use in a lot of details, right? So you should take a lot of images, take a lot of samples, and see what's happening in order to understand whether your actual model has learned something useful or not. So here we can clearly see that the model is looking in the parts that it is supposed to look in. I'm not sure if the eyes are the most, discriminative features of the face of the dog, but that could be the case. Using this guided backprop, we can also see that the model is focusing on the eyes a lot, but it also focuses on the rest of the face in one way or another. But the most important part is that it does not at all focus on the background, and it focuses only on the parts that actually matter. And this is the main difference between something like, what is it called? Lime and what is it called? And GradCam, right? So Lime just tells you, it's quite noisy here, right? So I'm not really sure that I can trust the results of Lime as an interpretability model if I use it with just 100. Okay, so if I use it with just 100 samples, it's just not enough, right? It's not enough to actually give me an explanation on what the model is looking at. But if for some reason I wanted like to just use Lime very much like to the best, then I should increase this number to like a much higher number. And I believe the results should look something similar to this. Do you guys have any questions maybe? All good? Yeah, so since we finished the lab, I just want to actually now run the code because I ran it like yesterday and it took a lot of time, but I just want to run it with you guys to see how fast it does. So here we're like training the boosting classifiers. Let's see how it goes. Wow, so yeah, there is a gender pay gap. Yeah, it's quite slow. Let's just skip these parts and go to Lime versus, yeah, this is Lime, for example. Let's just go with Lime just to see that actually Lime is much slower than GradCam. I'm sure you guys already know this, but it's just nice to actually see it. And let's try with, instead of, no, not this. What is it? Yeah, number of samples. Yeah. Oh, wow. Okay. I went a little bit overboard. Yeah, okay. It is super slow. Am I using a GPU? Oh, I'm not using a GPU. That's why. It's... Yeah, you see it's stuck here. It's gonna be stuck here for a long time. Let's pause and make this, I don't know, just 1000 and see how fast it goes. So for 1000, I'm expecting it to be quite fast, right? Which was nice. Let's try, what have I done here? So this is for 1000. Let's go for 10,000. Okay, it was quite fast too. The results have changed a little bit. Posting, post, NNTP, edu, lines, and there. Okay, let's go a little bit higher and make the number of features to 20. So this is definitely going to take a lot more time. I want to see if the model actually picks up on Darwin as a good clue for atheism, right? Does it? Wow, it does not pick up at all that Darwin is a clue for atheism. Thanks is a clue for Christianity. That's good. Okay, that's nice. So it did not pick up on Darwin as a clue for like atheism. This clearly means that it's not a problem of Lime. It's most likely a problem that our model is just basically not that good yet. So our model is just not perfect yet. It doesn't have a good understanding of what's happening in real life, right? Now let's go for Lime for images, right? How much time did it take? Let's see. 27 seconds. Okay, that was fast. Let's try it now for images. Images 1000. Let's go. Yeah, it's saying 1.12 seconds. Probably if I activated like CUDA, it would be much faster even. Let's just do it and see what happens, right? And this we make it 100. Yes. How do you say run all run after? Yep. Let's see. It's downloading the data. Looks good, looks good. It's training the model. Okay, that's okay. Nice. Okay, this moved fast. Oh, it took 5 seconds to do, wow, to do the interpretation on 1,000 different images. That's awesome. That's not bad at all. Let's go for 10,000. How much would that take? It would take 1 minute. Not bad. So this is the JSON that I was telling you guys about. So it's just basically class index, class name. That's it. And this was 259. What is 259? I think we could just search for it here. 259. Pomeranian. Let's check what Pomeranian is. Oh, so it's correct. Okay. So it's a little bit slower. Keep this image in mind. And let's see what the new image looks like. Okay, so you see the new image is definitely a little bit better. Just because we used more samples in Lime, we are getting better on interpretability of it. And now this is clearly more accurate, right? So here, Lime was telling us that the model focuses on the background, which I do not believe. And simply by increasing a little bit the number of images or the number of samples for Lime, we managed to get a better explanation or a more accurate explanation or more accurate depiction of the performances of our model. If we want to get something actually extremely accurate, we should go even higher, right? But that was gonna take like 10 or 20 minutes, right? So we're not gonna do that today. Wait, this thing I've done probably something here. Yeah, it's okay. Now let's run GradCam. So this is not GradCam. This is just downloading the model. So this is just downloading, what is it called? I don't know which model it was. VGG, yeah, it was just downloading the VGG 19, right? So all of this time here, it was just downloading the VGG 19. Sorry, let me just now go back to Lime here, to grad. So if I do it again, now it's not going to download from scratch. And as you can see, let me just remove this part too. So the image writing does take some time. Let's do it manually. Python print time. Yep, this looks good to me. Current time. So what I'm gonna do is I will call this here. This is the current time. And then we call it again here when we finish GradCam, and we see this is start time. And this is end time, just to see how fast it actually is, right? End time, end time, end time. And we will do print total time equals, and then end time minus start. Let's go. So this is the start time. And this is the end time. We cannot do, okay. So it's creating, it's converting it to a, string. Where can I do that? Here it is. Yeah. Now I'm guessing I shouldn't even include this part in it. Let's exclude this part, because all of this part is doing is just loading it to the GPU, which is not really. And image reading, let's not include image reading either. Let's only include, what is it called? The GradCam. Just GradCam. No image reading, no nothing. Just GradCam. Let's see how much it takes. Total time is 0.001. So it's like 1.8 seconds, I think, right? This is 1.8 seconds? Yeah. So it's 1.8 seconds and you have your explanation. Whereas and you have a perfect explanation, not just any explanation. You have an absolute perfect explanation of what your model is doing. Whereas when we go for Lime, if we want an actual good explanation, we should wait for 10 minutes or 20 minutes. Even on a very good GPU, right? It still takes a lot of time. So that's mainly it for today's lecture or for today's lab. Do you guys have any questions?
No, not really.
Okay, so if you get any questions in the future, just please text them or just contact me however you want. Have a great week. And do we have a lecture on the weekend?
We don't remember.
I will check and tell you guys. So thanks a lot.
Okay.
Have a great week. Bye-bye.
Thank
Bye-bye.
you. Goodbye.
Goodbye.